here is a problem, and I will tell you from the start that only 20% of the students who took the particular SSAT physics test upon which this question appeared, that only 20% got it right. It's not an easy question. And so here I've drawn 4 buildings. This is the building, the ground, top of the building. The building's height is h. Here I launch a ball straight out at velocity v. Here I launch it straight up with velocity v. Here I launch the ball straight down with velocity v. And here I pick some random angle called theta, and I launch the ball at theta. The question is, which of these cases has the largest landing velocity? And remember, the landing velocity is the forward velocity and the downward velocity added together using the Pythagorean theorem, hint, hint. And which of these cases has the greatest landing velocity, or are they all the same? Pause the video and then give it a whirl. So pause the video now, touch the video, get the box up, hit pause, 2 vertical lines, and give it a try. Okay, I'm going to assume that you gave it a whirl. And I'll just take this tape off that covered part of the answer, because I didn't want any peeking. And here is what the smart guy in class does. This would be I when I took physics. It's not necessarily good to be the smart guy, because there are other things you could be and do better on the SSAT than being the smart guy. So the smart guy says, well, these 3 have specific angles, but this one is being shot at some angle. So I'm going to work with this one and see if theta affects the landing velocity. If it does, then I should be able to say here theta is 0, here theta is positive 90, here theta is negative 90. So I should be able to just analyze this guy, and then I can analyze all of them. So the x velocity, you need trigonometry. This velocity here is v cosine theta, and the downward velocity is v sine theta. That's, you have taken the time to break this up into 2 components, vx and vy. And I've defined downward as positive. And the big 4 says that the distance, which is h here, is 1/2 gt squared. So h is positive down, so g is positive down, plus v sine theta times time, because this has to be the y velocity, initial. And now I have to solve a quadratic. I bring h across and I solve the quadratic. I have this as you know, little a, b, and c. So t, the unknown, will be negative b plus or minus the square root of b squared minus 4ac all over 2a. Where a doesn't mean acceleration here, it means the unknown in front of the squared term in the quadratic. So I did that. I got this. Because b, negative b, has this negative sign in front of it, I know to use the positive sign because the time has to be positive. It'd be foolish to pick the negative, because negative time doesn't mean anything. We don't have a way of going back in time yet. Be nice though, wouldn't it? Just have a time machine and go back and change things. Like you're riding along in your car and you remember something really stupid that you did in like the 5th grade, and you try to scream it away. Like, ah! I can't believe I did that. Ah! You behaved some way, you did something, you know, you want to change it. But it'd be great to have a time machine, go back and, well, I don't know, like buy a Gutenberg Bible for, you know, the equivalent of $1. Sell it for millions. Hey, it's a dream, right? Physicists can dream. I don't think that's going to be possible. Once you've studied modern physics, you'll kind of understand why. But I took this quadratic and I said, since time has to be bigger than 0, I get negative b plus the square root of b squared minus 4ac, minus 4ac, there's a minus sign here, so minus 4ac will be positive 2gh. And then I used the velocity of y has to be the initial downward velocity plus at. And so I found out what the y final velocity had to be, which was this. And then I used the Pythagorean theorem to find the total landing velocity. This takes a couple minutes, right, of algebra. And I get the square root of v squared plus 2gh. The landing velocity is not a function of theta. Kind of interesting. So I can't go and analyze these three. I have to do them separately. So I'd have to go and do the same kind of process 3 more times. Since there's 75 questions in an hour, that means about 48 seconds for a problem. So we must be missing something, because every question is doable in 48 seconds or a minute, because some questions only take us 15 seconds to do. So we could save up some time, but if you can't do it in under 2 minutes, you're definitely missing something. So this is what the smart guy does. This is what I would have done. Smart kid in class. So V landing is that for the theta case for the smart kid, not a function of theta. So maybe A, B, C you might guess are the same, but the wise kid in class looks at these problems and says that the work energy theorem says that, which comes from Newton's second law being multiplied by distance, that F net equals ma, that by carefully doing the algebra on Newton's second law, you get the work energy theorem, which we've already talked about, that the work done on the object that we're launching, and we're not touching it, so the work done is 0, is the change in the energy, and there's potential energy and kinetic energy, plus the work done by the object, since there's no air resistance and no friction. This guy is 0 and this guy is 0, and energy is conserved. So if energy is conserved, that means that the landing energy has to be equal to the starting energy, and every one of these cases has the same kinetic energy and the same potential energy, so the landing velocity has to be the same by the work energy theorem. So we just turned a 2-minute romp through the big four into a 20-second application of the work energy theorem, which is what the wise person does who studies. Smart kid wastes time, wise kid studies and knows what to do.